So this is supposed to be 19 D.2, solids of revolution. And I just realized that there's actually another example from D1 that I skipped. So I'll go ahead and do it on this one. So that was example 12. They've got one arch of, so they've got y equals sine of x, and we're going to rotate that about the x-axis again. And we just want to find the volume of the revolution. Of the solid. Find the volume of the solid. So we're doing one arch of y equals sine of x. Well, we know sine goes from 0, it goes like that. One arch is from 0 to pi. And then we're simply going to be revolving that. So it's going to look, it's kind of like a football, actually. Imagine the football. So the integral sets up just, it's still the disk method, because same situation we've been having lately. So the volume is pi from, in this case, 0 to pi of sine of x, that's your r, but you have to square it, dx, pi r squared. And this is where we have the fun task of integrating sine squared, because you can't use the power rule, because the power rule is only going to work if it's x squared. If you try to use the u substitution, you would have to make your u sine of x, and then when you did du, you'd have cosine of x dx, but there's no cosine of x in this integrand, so we would be stuck. So then you have to think, oh yeah, how do I do this? And we've done these before. We actually did one on the test. Remember, you have to use that identity for sine squared. It's called the power reducing formula. And if you're confronted with one of these on the IB exam, let's pretend that we're on the IB exam and they don't give you the formula for sine squared, but you do have your formula sheet. So on the formula sheet, I have to remember, I think, let me go get that formula sheet just a second. Okay, on the formula sheet, under trig, okay, they do give you, this is 3.3 on the formula sheet, they give you the cosine 2 theta down there. It's the last one on that little section. And they give you these various versions. There's 3 versions of it. And you can, in a pinch, derive these. I usually do because I don't memorize these. So you look on your formula sheet, you see that. And so the one you want to use is the very last one because it deals with sine squared and we have sine squared. So you want to take that very last one and you want to solve that for sine squared. So hopefully you can do that in your head. I'm going to do it in my head. Sine squared of theta will equal cosine of 2 theta minus 1 and then divided by negative 2. And a lot of people prefer to write it like multiply top and bottom by a negative. Oh no.
This is an Alice drill. This is an Alice drill.
I guess disregard that. Actually, oh, I can't turn the volume down. Just ignore that. I'm going to keep working. So I'm going to distribute my negatives. So I'm going to have 1 minus cosine 2 theta over 2. So it changed the sign. Okay. I'm going to erase all this. Okay, that wasn't too bad. Okay, back to my integral. God forbid we ever have that happen. Anyway, back to what I'm doing here. So sine squared of x is, there's my pi, I brought it down and bring my 0 and pi along. Sine squared is 1 minus cosine 2x over 2 dx. Okay, now we can integrate that. I am going to, the best way to integrate this is to break it into two fractions. 1/2 dx minus, same thing. Let's just do, well, there's a pi there again. Negative, so there's a minus out front. So I'm, oh yeah, I've already got the minus. Never mind me. I guess that Alice drill kind of threw me off. Okay, so I split it into two fractions. This negative here is right here. The pi out front is being carried along to both. Everything looks good. Oops, oh my gosh, I broke my pen again. Oh dear. That's okay, I can fix it. It's a very nice little pen. Okay. Okay. I'm going to take that pi all the way out front. The big bracket. So we're going to integrate 1/2 dx, which is 1/2 x. I'm going to put these all back together again because they have the same limits. And, okay, so I've got that. And then, so that pi, this pi here, I've got it out front now. Then I've got this 2 here, so I have to bring that, and I've got the minus. I've got minus, and then I've got the 1/2, that's the 2 from that. And then the integral of cosine is sine of 2x. But then I have to divide by this 2. Derivative of sine is cosine, so we're good there. And we're going to evaluate from 0 to pi. Okay, bring the pi along. So this is the same as, oh, that's supposed to be a 2. I don't know what. I guess I got thrown off there. Okay, that's better. Let's fix this and make this a 4 too. All right, we're good. Great. So pi's out front, and then I'm going to evaluate this from 0 to pi. So I'm going to have 1/2 times pi minus 1/4 times sine of 2 pi minus, parenthesis, plug 0 in, so that's going to be 1/2 times 0 minus 1/4 sine of 0. Now this is 0, and sine of 0 is also 0, so all that's 0. Make sure you check that though, this isn't always all equal to 0. Sine of 2 pi. Hey, that's 0 also, isn't it? So that's nice, that's gone. So we've got 1/2 pi squared. And that's units cubed. By the way, I should have been checking these better, like on the calculator, so let's check this. And there was a problem back there that we could have checked also with a geometry formula, and I failed to do that as well. So, oh, I don't need that. I need to go to blank screen. Clear that. So I'm simply going to go back to my original volume here and just put this in. Pi Fn, math 9, and I've got sine squared, sine of x, close, and then squared, so that's how you enter sine squared, comma, x, comma, 0, comma, second pi. And I'm of course going to get a decimal. 4.93, the IB way. And let's check 1/2 pi squared. 0.5 times second pi squared. And that had better equal 4.93, and it does. Great. So it's all nicely checked. And then we have the washer method. The washer method happens when, oftentimes, when you're revolving two functions, usually. So let's make up, we'll make up f, how about that? And then let's make G interesting like that. I don't know how interesting that is. And let's say you were to revolve that entire region about the x-axis. So I'm going to reflect F about there and G about there, just so you can get a sense of what this is going to look like from A to B. And when I revolve it, so this is going to be didn't do too good a job of that one. Kind of imagine top of this thing. So it's actually kind of this really cool looking container, because this middle part in here is all open. And so it's this container on its side that kind of a cool looking, I like that container. I wouldn't mind having a pot, like a flower pot looking that way, that shape. That's pretty cool. And we are going to get the volume of the solid itself. So when we're finding, imagine the solid, like the material, if you were making a flower pot, what's the volume? And you were pouring, say it was concrete, and you're pouring concrete into a mold to make this flower pot. The amount of concrete is what we're finding. We're finding the volume of the actual solid part itself. And, oh man.
Thank you, Palmer High School. Let's conduct our Alice drill.
I'm going to do a slice.
Thank you for your participation. Hopefully you had some conversations about a variety of options that you had. Please remember that in a violent intruder situation, the situation would be very fluid. You may have discussed locking down in place. You may have discussed evacuation. You may have discussed preparing yourself in case the encounter was necessary. If the intruder accessed the area that you weren't able to escape. Being prepared and having these conversations are the best way that we can possibly mitigate any injuries or casualties should the worst occur. Thank you for your participation. Have a great rest of your Friday.
Okay. So I drew a representative slice up there in blue, and then I brought it down below where you can see it better. And each slice is actually a washer. So thus the washer method. And in order to do the volume, it's going to be, again, the integral. And we're going to be finding the volume of each slice, which is the volume of this washer. So to get the volume, you would find the volume of the big cylinder minus the volume of the hole, or the little cylinder. So that's going to be, like, here's the big R for the big radius, and little r is going to be the radius of the little one, the hole. And so the volume of this washer is pi times, oh, there goes the bell, pi r squared, which is the area of the big circle, minus pi little r squared, that's the area of the little circle, and then of course we have to multiply that by the thickness dx. And we're summing all those up, so therefore our integral is pi times big R squared minus little r squared dx from A to B. Now it's lunchtime, so I'll just finish this problem up before lunch. The book, just give you the formula the book uses. A to B, f of x squared minus g of x squared dx. Or y upper, here, volume equals pi integral A to B, y upper squared minus y lower squared dx. So now that we have the idea of the washer method, we can go ahead and do an example, example 13. This is our only example, I do believe. I should probably double check. Yeah. Okay, so on this one, we're going to revolve y equals x squared and y equals root x about the x-axis. And that region that's enclosed by those is the region that's actually going to get revolved and form the solid. So when you graph these, we know they both go through 0, 0, and they actually both go through 1, 1. And y equals x squared is concave up. and y equals root x is concave down. So they look like that. So this region here is going to get revolved about the x-axis so that you can get a sense of what it looks like. This is going to come down. Like, whoops, I missed, oh well. And this is going to be just kind of a really funny looking solid. This is really trippy looking bowl thing. Anyway, without further ado, let's find the volume. So again, it's pi r squared, but it's big R squared minus little r squared this time. And we're going from, they intersect at 1, so we're going from 0 to 1. And we want to do the outer radius minus, or outer radius squared minus inner radius squared. So the outer radius is from this axis of revolution up to the outer one, and now the outer one is root x. So we're going to have to square that, minus, and then the inner radius is from the axis of revolution up to the inner one, which is x squared, and we have to square that. So we've set it up using the washer method. Now, I'll clean this up a little. That's x minus x to the 4th dx. So when we integrate, we're going to have pi out front, x squared over 2 minus x to the 5th over 5, and we're going to evaluate that from 0 to 1. Unfortunately, those are easy to evaluate, thank goodness. So pi comes along, plug 1 in, you're going to have 1 squared minus 1/5, and then minus, and then you're going to plug 0 in. So that's just 0 minus 0. So I don't have to worry about that. Let's get a common denominator here. Times 2 times 2 times 5 times 5. So I've got pi, and then I've got 5 minus 2, so that's 3/10. So the answer is 3/10. Sorry about that. 3/10 pi units cubed. That's a, what is that in decimal? Well, 0.3 times, so it's going to be around 1 times pi. 0.942. Now you could check your integration on the calculator if you wanted to. And that concludes not only section D2, but also the entire chapter.